Welcome to the third lecture in Introduction on Lattice-Boltzmann methods in the winter term 23-2024. Today we go on with still the theory in the kinetic theory and its connection to actually the continuum theory. So we go from now our Boltzmann equation, or our simplified Boltzmann equation, which we derived last time as the BGK-equation. We go to the hydrodynamic limit. This means from the Boltzmann equation essentially going to the Navier-Stokes equation. So how does the Navier-Stokes equation drops out of the Boltzmann equation? So we don't use the full Boltzmann equation, but we start already with our reduced Boltzmann equation, so the BGK equation. And I write it here now without forces. We can talk about forces later, but first write it without forces. So we have the time derivative of our one particle distribution function f plus the kinetic advection operator, which is the microscopic velocity times this spatial derivative. And now this is the left-hand side of the Boltzmann equation, and what makes it the BGK equation is the simplified collision operator, which just takes the equilibrium distribution minus the incoming distribution and divides this by tau. So this is the BGK operator, the BGK collision operator, which is very simple. So the equilibrium distribution is a Gaussian distribution. Yeah, so everything is a Gaussian distribution. So we have already derived in the last lecture how this looks like. And now the remaining question is this: what is tau? Okay, so obviously, if we look at this equation, then we can say that this is a rate equation where the non-equilibrium contribution is destroyed. Yeah? And this tau equals a time scale at which this happens, and this is then, of course, a time scale at which we approach equilibrium. So there's a time scale for the return to equilibrium if we start outside of equilibrium. Okay, maybe. So why actually return? I was just thinking. Return means we have previously been in equilibrium, right? Yeah. So this may be a little bit confusing, but actually I mean it that way because we assume that when particles collide. Yeah, and because we are dealing with statistics, yeah, when particles collide, the outcome of the collision is completely random, so statistically they will be in local equilibrium at this place. Now, what is very important to distinguish in kinetic theory is that there is a global equilibrium where everything would be dead, so velocity zero and so on. And there is a local equilibrium, and this local equilibrium depends on the local velocity and the local density, and probably on the local temperature, right? And because this local equilibrium depends on quantities that are not constant everywhere, they have different equilibria in different places. And then on the left-hand side, we have an advection operator. Yeah, so time a transport operator that transports the distribution from one place to another place. And then when they are combined in this other place, they are no longer in equilibrium because because the different equilibria in the original places were different. Yeah? So when you combine them, they are no longer in equilibrium. And now comes a collision and they return into equilibrium. This is what we mean by a return to equilibrium. Okay, so as I was just indicating what happens when particles collide, we assume they go to equilibrium, and this actually means that they lose their memory. Equilibrium is the state of least memory, so to speak. You see, if you want to describe an arbitrary distribution, you need, in principle, you need all the positions of all the particles that you have, right? To have an arbitrary distribution. But if you describe equilibrium, you just need its velocity and its temperature. Yeah, so you have a very, very large number of particles potentially, but you have only 4 parameters describing everything, right? So now you go from non-equilibrium, we have a lot of information, to just 4 variables. So this means you are losing a lot of your information, so you're losing your memory on everything that happened before. So on the motion that was before the collision. Okay, a little picture. Say here's a position A, and we have so this is a particle, and say this was the last time, in this position A, this was the last time the particle collided. Now it makes a free stream to another position. This free stream goes a distance of the mean free path lambda. Then here, say, okay, so there was another particle colliding, and here is again another particle colliding with this, probably coming from here. And after this particle here goes to any other random, in another random direction, while the blue one also moves, for example, this way, right? We don't care about the blue one, we only care about the black one. Yeah? In kinetic theory, we only deal always with one particle and regard everything, all the others, as a statistic. So this means for us, okay, let's write down. So this lambda is the mean free path. I just don't remember whether we already introduced this. So there's the mean free path between collisions. Then we just had the tau. So what is the tau? The tau is actually the mean free time between these collisions. And then we have a speed c, which is the mean. Okay, a speed is a vector, right? So this is a mean, so it's the magnitude of this vector. Because it can go in any direction. The mean particle velocity. The particle velocity is distinctly different from the velocity of the fluid, of course, as we already discussed. Yeah? So what is it proportional to?
Which part?
the particle velocities, what physical, easily observable quantity is related to the particle velocity.
Temperature.
Yeah, this is correct, but it's not. But this is also correct, but they are not. You know, if you want to need the temperature, if you want to get the temperature, you need to know about the Boltzmann constant. If you want to have the energy, you need to know how heavy the mass of your particle. Something that's a velocity that can more easily be related to it. What velocity is?
Time.
No, time is not velocity. The speed of sound.
Okay.
Yeah, the speed of sound is not, quite annoyingly, it's not absolutely exactly the same, at least in real physics, because there are other forces and internal degrees of freedom and so on that change the speed of sound a little bit. But the mean particle velocity is at the very least proportional and not much different of the speed of sound. So, in principle, you can easily measure the particle velocity, yeah? Because you can easily measure the speed of sound. So you go to the Alps and you shout, and then you wait until it comes back, you know the distance, and now you can compute the speed of sound, right? So this is how it's pretty easy to get to this quantity. Okay. Now this lambda is a distance. So what is lambda? Lambda obviously can be expressed as the speed at which the particles move times the time between collisions, right? So this means we can of course express tau. Tau then is this lambda divided by c, obviously. So this is because, and this is okay. We need to know the speed of sound. So this is something we know, and okay, maybe no. I think this is still correct. Yeah, this is correct. And we need to know the speed of sound and we need to know the distance. So, in principle, this means this tau, there may be a factor in front of it, yeah, is proportional to the mean free path divided by the speed of sound. Okay, so now let's try to get us a little closer to the continuum theory. And in the continuum theory, we will, especially in fluid dynamics, we'll often talk about dimensionless numbers. So, you probably heard about the Buckingham theory.
Yeah.
Okay, you heard about it, so I don't need to introduce it too much. Buckingham, it's also called, so Buckingham, of course, didn't call the Buckingham theorem Buckingham theorem, so this is called the pi theorem, yeah? This is the generic name. Actually, I prefer to call things by names that do not include some people, because whenever something is called after somebody, you will later find out that this was not the inventor of the method. Like Lattice Boltzmann. Boltzmann, of course, did not invent Lattice Boltzmann, yeah, but he of course invented the Boltzmann equation, yeah. I guess so, yes. So Boltzmann is a person who has too many things named after him. Yeah? So what should we? So you have a Boltzmann constant, which defines one out of only 7, right? Natural constants that we need. Yeah, the one after is named after him. He has several distributions: Boltzmann distribution, Maxwell-Boltzmann distribution, Stefan-Boltzmann distribution, and he has a Boltzmann equation. So what else? There are even more things named after him. So, okay, Buckingham and P theorem. So, without going too much into the detail, it's just that natural systems can be described by their dimensional dimensionless numbers. So by non-dimensional we should ask our colleague to be a little bit quieter. So when we have dimensionless numbers, of course, we can describe physical system with dimensional numbers, yeah? So what dimensional numbers do we have here? Usually we have a macroscopic, now we are a little bit in the macroscopic world. We have a macroscopic velocity, u, and we call this the velocity scale. So the velocity scale, by the way, this is could be at first glance a little bit confusing, yeah, because the velocity scale is not necessarily a velocity that actually is somewhere, yeah. This is just the velocity that we consider as being characteristic of our problem. So it is a scale, yeah. It's you can describe our distance that we have here in meters or in feet. Yeah, so this is doesn't mean that when we measure the distance in feet, you are further away from me, right? It's just something that we normalize to. So, for example, we could say that this here is just, for example, 1 meter, right? And then we have another quantity that is the size of the system. This is L. And again, this is something that we consider to be characteristic of a scale. So we could simply say, for example, this is 1 meter. Yeah? And then we describe our actual problem. And somehow in fluid mechanics, the most common application in fluid dynamics still is measuring the drag on vehicles. I mean, in computational fluid dynamics. This is what computational fluid dynamics was invented for, and this is still what 90% of computational fluid dynamics does, is you have a vehicle and you measure the drag. Yeah? So this vehicle has a velocity u, and it has a size L. Yeah? So, and they are now characteristic for our problem, and we want to describe this problem now with dimensionless numbers. And the dimensionless numbers we are now using without deriving them from the Buckingham theorem, because I guess this is something that we learned somewhere else, is the Knudsen. Have we had the Knudsen number in the previous? No. Okay, it's the Knudsen number. The Knudsen number is the mean free path divided by the characteristic size of our system. Yeah, you see pretty easily that this has no dimensions because it is size by size, right? So this guy we call Knudsen number. So these numbers are all of them are named after guys, by the way. Yeah. I don't even know whether there is one that is. I mean, guys in the sense of male, you know, white male, old white male persons with a big beard, usually. It's in particular, the next one, Mach, the Mach number. Mach was a guy with a very big beard. Yeah? So Mach is defined as the velocity scale divided by the speed of sound. Yeah? This is the Mach number. And I think the Knudsen number is probably something that is new, but the Mach number is something that everybody have heard about. Yeah? So by the way, when they say that the velocity of is sometimes not completely correctly used, because when you say the velocity of the Concorde was Mach 2. Is of course not correct, because this is not a velocity actual, that's the Mach number. Of course, the implication is if you know the speed of sound, you know the velocity from the Mach number, but the Mach number, but the speed of sound is not a constant. So you cannot define, you cannot take the speed of sound as a physical normal for measuring a velocity, because your normal has to be constant. Yeah, so you cannot tell from the speed of sound from the Mach number what was the actual velocity. Of course, the speed of sound is not dramatically changing usually. Yeah. Yes, but the Concorde usually, if it's supposed to work, then it usually is in air. Yeah. The problem is rather than when it's flying very high, so the temperature around it is very different, and as you correctly said, and the speed of sound is of course related to the square root of the temperature. So, okay. The thing, of course, is this is the square root of the absolute temperature. So a few degrees difference under the square root, if we are in the range of 300, doesn't make a big difference. Yeah, but still, it's not really the same. So of course, I mean, as I just said, you can write these things in the other way. I mean, this is of course absolutely trivial. Yeah. So you get the lambda, if you know the Knudsen number, times the length scale, and you get Cs if you take U divided by Mach. So why do we need this? We need this because tau is equal to, up to probably until up to a parameter lambda divided by tau. So if you put this in, what you see is that you come out with Knudsen times Mach times your length scale divided by your velocity scale. So this is tau. Tau can be expressed by length scale and velocity scale times the Knudsen and the Mach number. And now we look at some limiting case. So we have to look at a limiting case because we want to go to the continuum theory. How does this behave in continuum? Oh, okay, I write cases instead of case because there are two. So what we have in continuum means we are no longer interested in the existence and behavior of molecules, right? So what will happen in continuum? Continuum would be obtained if the size of the system is very, very much larger than the mean free path of a particle, right? Otherwise, you are influenced, obviously, by molecular processes. So, and this means that the Knudsen number has to go to 0. Then the next limit is we just look at slow flow. Yeah, because we now have a velocity, we have a speed of sound, yeah, and of course we could have the speed of whatever we put into it could be 3,000 times faster than our speed of sound. Then we would have a completely different behavior than when the flow is actually slow. So what happens when the flow is slow is that air and in particular other media like water act as pretty much as if they cannot be compressed. Yeah? So this leads to an incompressible limit, and this would be if the velocity is much, much smaller than the speed of sound, and if this happens, the Mach number goes to 0. So now you see this is our limiting case. Knudsen number going to 0 and Mach number is going to 0. So what happens to tau? Tau apparently goes to 0 too, right? Yeah. Okay, let's look at this incompressible continuum limit of the BGK-equation. And yeah, so now we are using our theory of moments that we've introduced the last time. We are using there are countable moments now not on the distributions but on the equation. Okay, I write the BGK equation just to get familiar with it again. So this is our BGK equation. F EQ minus F, and we divide this by tau. And now this operator here, I specify this operator as xi. So the xi scalar product of nabla, and this is now a three-dimensional operator with the velocity the same way as we introduced last time, xi, upsilon, and theta as the three components of the microscopic velocities into dx, dy, dz. So this is our kinetic advection operator. Means we can write the BGK equation in a more explicit form as dTf plus xi dxf plus upsilon dyf plus theta dzf, and this goes into f equilibrium minus f divided by tau. No, before you write it down, I do it a little bit different. I bring this on the other side, I take minus and put this to 0. Yeah, so I put everything on one side that I have it at 0, and then I take this thing and produce countable moments of this. So what again, so reminder last time, countable countable raw moments. Again, this is the main thing that we use here. We define the countable raw moments, yeah, with indices a, b, c, m, a, b, c, as the integral from minus infinity to infinity over the distribution f, c by the power of a, epsilon by the power of b, and zeta by the power of c, and this all integrated over all velocities. Yeah, three-dimensional velocities. Now, instead of using this on the distribution, we will use this on the actual equation on the distribution. Yeah. So the countable, we take the moments of the BGK equation. Which means, so we take the integral from minus infinity to infinity, and then we have the c by the power of a, epsilon by the power of b, and the zeta by the power of c. And then simply we put the left-hand side of the equation that we have here into it, dt f plus dx c f. So you notice we get lots of disturbances today from all sides, I noticed. I actually turned off the internet here so that I don't get disturbed. dy epsilon f plus dz zeta f minus f equilibrium minus f divided by tau. Let's divided by tau, and we integrate all of this over the entire space. So one thing that you may notice is that I put these things here under the into the derivative, right? There was no particular reason why I did this, other than I want to show that this is actually possible. You see, these microscopic velocities, they are degree of freedom. They are no. The microscopic velocity does not depend. So they are independent degrees of freedom from the position, right? So they do not depend on x, y, and z. Yeah. So it does not matter whether they are in front or the derivative or inside the derivative. And this is a very important property of the kinetic advection operator, because the continuous advection operator that we know from the Navier-Stokes equation behaves in a different way. Because then there is the velocity, the actual macroscopic velocity instead of the microscopic velocity. And the macroscopic velocity is a function of space. So there you cannot exchange it, but here you can exchange it. Yeah? So this is a very important difference. Now, this is all we have on the left-hand side, and on the right-hand side we have 0. Yeah? So please forgive me, I'm not writing the integral over 0, because I already know that the integral over 0 will turn out to be 0, right? So I just write all of this together as 0. Okay, now in this thing, let's just some notes. All terms are linear, so this is different from the Navier-Stokes equation. And these guys here, they do not depend. They are not dependent on x, y, z, and t. So this is very important, because this actually means that we cannot only take the ones down here inside the derivatives, but we can also put what we have in front here inside the derivatives, right? Because there's no dependence. Did you get this? Yeah? So, now if we put them inside, what do we obtain? We basically obtain the definition of the moments that we have up here, right? F times the kernel, so the monomial of the microscopic velocity, yeah? So we get this inside the differential operator. We get the definition of the moments. So when we do the integral, yeah, if we put the integral also inside the differential operator, we actually get the moment. So we can rewrite all of this as an equation for the moment. So because we get dt m, so what do we get for the first thing here? So here we have no other velocity, so we have just f. So this will be the time derivative of MABC, right? So it's getting more interesting. We're coming to the dx. dx has a xi already inside, and then there is a xi by the power of a, and a upsilon by the power of b, and then zeta by the power of c. So what moment do we get here? So how many times do we have xi? We have this xi by the power of a, and we have this here. Yeah, so how many? Well, no, not two. Xi by the power of a times xi. So it's xi by the power of a plus 1, right? So this is a plus 1. And the others is just b and c. So now you see we count up this a by 1. So then we get dy. What is here with dy? Here we have xi just by the power of a. Then we have upsilon by the power of b plus the upsilon here, which is one more. So it's b plus 1, right? Yeah, and c. And now you learned it. This is dz m a b c plus 1, right? So, and the operator here does not include, the collision operator does not include any further, anything further, so it will just turn out to be minus m0, sorry, not 0, it's ABC equilibrium minus MABC, and this guy divided by tau, and all of this together is still 0. Interesting. Now we got completely rid of our integrals, right? Yeah? So, and we get what we call a moment chain. So you see, we have not specified what A, B, and C is, yeah, but we see there is, so we get an equation that's pretty much independent of what they are. Now let's look at our moment chain that is coming out of this. So now, if we want to have specific equations, obviously we need to specify what we mean by A, B, and C, right? So let's say A is start from the beginning. A is 0, B is 0, and C is 0, right? Okay, what would it mean? Now we need to know what are these moments. The moment m00 is the integral from minus infinity to infinity, xi by the power of 0, upsilon by the power of 0, and zeta by the power of 0. So obviously all of this together gives 1, right? Things by the power of 0 is 1. And this into f integrated over xi. So now this thing here is the density. Now it's the question, we are a little bit lazy in kinetic theory with this density, because what we usually mean in fluid mechanics as density is mass density. Yeah, so you get the mass density when you multiply the probability of finding a particle with the mass of one particle, right? So this, in that sense, is not the mass density, but the density of particles. So it's a number density. Yeah, and you can turn this number density into a mass density if you multiply it by m. But usually we are a little bit lazy here and say, so mass of particle is 1, right? And don't care that much. And this is also the reason why some of the equations that you find in Lattice Boltzmann publications may not turn out to be dimensionally consistent. Yeah, because we just assume mass is 1 and not mass is 1 kilogram or something like that. Yeah. Okay. Now we look at what happens with our equation. So the equation would be the time derivative of m000 plus dx. Now we count up the countable moments. So this is why the countability of the countable moments is so useful. Yeah. So we have 0, 0, 0. So the dx derivative is 1 more in the next index. The dy derivative is 1 more in the second index, and the dz is 1 more in the third index. And all of this, I put the collision operator again on the other side, comes into m000 equilibrium minus m000, and all of this divided by tau. Now we need to know what is this, so they look similar, and maybe you already know what they are. What are they? So we do the integral, f, and multiply by xi by the power of 1 over all the directions. So this will be the density, particle density, times the macroscopic velocity in x direction, right? And very similar, because they look exactly the same, would be m010 is the particle velocity in y direction, and m001 is the particle velocity in z direction. Okay, now m000 being rho, the density, this thing is conserved. So we are not generating particles, right? So this thing is conserved, and when it's conserved, it means that the equilibrium equals the moment itself. So when the moment itself equals the equilibrium, what happens to the right-hand side?
In this equation?
Yes, to the right-hand side of that equation.
Yeah, it goes to 0.
It goes to 0. So this will just disappear. So the equation that we end up with is dt rho plus dx rho ux plus dy rho uy plus dz rho uz equals to 0, which we can write in a more convenient format as dt rho plus nabla onto scalar product rho u, so divergence being equal to 0. Do you know this equation? No? This is called the continuity equation. And it's used in fluid dynamics. So mass, this is, that's the continuity equation. You need this for solving the Navier-Stokes equation. The Navier-Stokes equation itself is not sufficient because it has a pressure term. Okay, we come to the Navier-Stokes equation. Let's go on in our moment chain. Let's count upwards. A equal to 1, B equal to 0, and C equal to 0. So what equation does this give us? So we get dt m100 plus dx. So what moment do we get now? We start, A is now 1, B is 0, C is 0. So the first moment here is m1. We take the time derivative of m100. What? No. Which one do we count up under dx? The first one.
Yeah,
so it will be 2m200. And here, under the y operator, we count up the second. So it will be 110, and here would be this set m101. Okay? And on the other side, we'll just have 100 equilibrium minus m100 divided by tau. So what's about this? Do you have any idea? We said that m100 is rho ux. So rho ux is, if you take the mass together with it, it would be momentum, right? Or it would be, because the particles all have the same mass, you should think about its momentum, not velocity. So if it's momentum, then obviously it's conserved, right? So what does it mean for m11 equilibrium if it's conserved?
Okay, equals to
and what does this mean for this? This again will go to 0. Now, can we now express this equation? We have a little problem, namely that there are these other moments, that we have to identify. So we have to identify, this is easy. This is why it's called a moment chain. So because we want to write an equation for m100, and this depends on m200. Right? And you can already from the structure of it, you know that the equation for m200 will depend on m300, right? So this is why it's called the chain of moments. So let's look at what this actually is. So m200, what is this? We have to express this as A equal to, B equals 0, and C equals 0. And now we get an equation for the guy, dt m200 plus dx m, so what? Which indices? m300 plus dy m210 plus dz m201. So by the way, when I started this they were, to learn this, they were all crazy names for moments. So somebody thought about, for every new moment that they found, they got a new name and defined it in a strange way. And now you can imagine how difficult kinetic theory, explaining kinetic theory was. Now if you use countable moments, everybody can learn it. It's not complicated, right? You just go on here forever. So now on the M200 equilibrium minus M200 divided by tau. Now, everything that we had before, right, was kind of conserved. Now you could say that M200, is this conserved? You know, it's a little bit confusing because, okay, actually it's not conserved. But there is something that is conserved. What is this related to? I think we had this already. It's related to the energy, right? M200 plus M020 plus M002. So in the old days, they would not count up the moments, they would define this as a moment because this is something that you know, this is the energy. And now they would try to write the equation with this kind of moment, and then you're very confused because, you know, it looks very complicated. Yeah? Because this is the energy. This has the advantage of being conserved. So when you write, if you write all these equations together and sum them together, then the sum of their collision operators will be 0. But for one individual, it won't be 0. Okay, so now we have to kind of dealing with this. What we want to know for our moment chain, yeah, because we want to have an equation for the velocity, right? You know that the Navier-Stokes equation is an equation for the velocity, so it's an equation for the first moment. And you see that this depends on the derivative of the second moment. So we actually want to know the second moment. How do we get to the second moment if we have this equation here? Now there is actually an advantage of the moment not being conserved. Because when the moment is not being conserved, we can solve this equation for this guy back here, right? And give an explicit expression for the moment M200. Now this is, so if I solve for this, I have to multiply by tau and bring the M200 equilibrium to the other side. I get minus tau and everything that is written on the left-hand side. So dt M200 plus dx M300 plus dy M21 plus dz M201. Okay, so now this is exactly what we have in this moment, and this we can plug into the previous equation. Very similar, without writing them down in. We also need the other ones that were in this equation, and the other ones in this equation were, for example, M110. Yeah, M110 again is not conserved, so we can do the same thing. Yeah, so we get here the equilibrium M110 equilibrium minus tau, and now because it's so easy, we can just write it down, right? This is M110 plus dx M210 plus dy M120 plus dz M111, right? So, and of course, the last one that we also had was M101. This is simply M101 equilibrium minus tau. Again, very easy, dt M101 plus dx M111 plus, wait, what am I writing? 201 plus dy M111 plus dz M102. Okay? Okay, now we need to know what are these equilibria, and this is something we've done already last time. Now I'm taking the equilibrium of M200, and this is by integrating the Boltzmann distribution. So it's the so this now simply comes from physics. So there is the Boltzmann constant in it. Here I have the mass. I divide by the mass because I've now using the particle density and not the mass density. Yeah, it's not so important. Times the temperature by the power of 3/2, I believe, and this into E by the power of xi minus macroscopic velocity u square times the mass divided by 2 Boltzmann constant temperature. So this is the equilibrium distribution, and to get the moment we have to multiply this by xi square. Yeah, because we are looking for M200. And then we integrate this. Okay, so when I integrate this function, I'm using Mathematica because I'm lazy and this looks difficult, and what I get out is the density K Boltzmann divided by particle mass and this into T plus ux squared times rho. So this is what I get. So similarly, similarly, M110 equilibrium. Okay, I'm writing it again. K Boltzmann T by the power of 3/2 E minus xi minus u square M Boltzmann T. So what do I have to multiply it with? I have to multiply this once with xi and once with upsilon, right? And then we integrate this over all the velocities and end up with rho ux uy. Shall I write the other one too? Okay, let's just do it. Is again all of this integral 2 pi kb divided by m, this into t, and this to the power of 3/2 e by the power of minus xi minus u, xi minus u, I mean, and this to 2 Boltzmann constant t. Now we have to multiply this with xi and with xeta in order to get this, and we'll have, obviously we'll have rho times ux times uz. I mean, this is obvious, right? Nature should be symmetric. Okay, now we know the equilibria, but we do not only have the equilibrium, we also have this later part, right, in our moment chain, and somehow we have to get rid of it, otherwise we cannot proceed. Yeah, I mean, it's very obvious. If we add them, we have to get an equation for them again, and they will depend on even higher moments. So the chain will never end. So how do we get the chain to end? And what we are now going to do is we are using this tau to end it. So what again is tau? Tau is equal to Mach times Knudsen times the size of the system divided by characteristic velocity. Okay, now you see, if we look at continuum theory, then continuum and incompressibility together, then the Mach number should be small and the Knudsen number should be small. So what we could assume, and we'll come to the point to see that this is not a good assumption, but let's make this assumption, that all of this together is 0, right? So then we assume a system that is very large. So very large, Knudsen, let's say Knudsen is going to 0, and that this would mean that tau is also going to 0. So if this is the case, all of what we've written here, will disappear, and we will only depend on the equilibrium. And so the moment chain is terminated. And then we can write down explicitly an equation, and this equation will simply be dt, the time derivative of m100 plus dx m200, now equilibrium only, plus dy m11 0 in equilibrium plus dz m101 in equilibrium, and we decided that all of this is supposed to be 0, and now we can plug in everything here, and this will be dt rho ux plus dx rho k Boltzmann t divided by m plus ux square rho plus dy of ux uy rho plus dz ux uz rho, and all of this together will be 0. Okay, now there are differential operators on products of terms, so what we would like to do is to apply the product rule to all of these guys in order to try to see whether we can simplify this. And this will give us, of course, so first of all, it will not simplify it, it will increase in size. Let's try to do it. So I already grouped the things like this, that what we observe is that very often we see ux here, right? So I'll put the ones with ux to the outside first, and for example, we'll have it here also, the ux, and this is then dt rho, right? Plus ux dx rho ux, and plus ux dy uy rho plus ux dz uz rho. So and now we have to do all of this in the opposite direction, plus, so I take different brackets here, rho dt ux, so this is the other part of the product rule, obviously. So what we have missing more, we have been missing rho ux dx dx ux plus uy rho dy ux plus ux rho dz ux. So all of them are just now derivatives of ux. And if you were following me in detail, you noticed that the only part that I've not taken now out is this guy, and I'll take the liberty of putting this guy to the other side, because this is the way the equation is usually known. So it's the dx of rho k Boltzmann m and this into t. So what we observe is that if we look at the term that I've written up here in this kind of brackets, that this is simply ux, so is ux in front of everything, and then there is dt rho plus rho. So this is the equation that apparently you did not know previously, but now I hope that you know it. Right? So this is the continuity equation. And we've
seen that in like a different form.
yeah, so this is the continuity equation, and we say that the continuity equation equals to 0, so the entire thing here equals to 0, meaning we can get rid of the upper part here, right? And the equation that now turns out of this, if we write it in a more convenient way, would be rho dt ux times rho u. So because we see there's ux, uy, uz, and all of them together act, so this is u times scalar product on nabla, yeah, ux times dx, yeah, on all of them acting on ux part, and on the other side we have dx rho k Boltzmann divided by m and tau. So is this now roughly going to be looking familiar? Starting to look familiar? Maybe not yet entirely, but yeah, it's getting closer to the Navier-Stokes equation. It's not the Navier-Stokes equation yet. So for example, this guy back here looks a little bit strange, but what we can do is we can look in the ideal gas law, right? So ideal gas law is PV is K Boltzmann T. So in our case, because we look at particle density, V is 1 over rho. That's the inverse of the density. So that means that P is rho K Boltzmann T. Okay? And M is a constant because it's the particle mass. So again, we can rewrite the entire thing. It's going to look a little bit more like the Navier-Stokes equation, but not yet. Rho u x, and now on this side we have 1 over m, so this comes because the rho, our rho does not include mass. If rho would include mass, you know, it would disappear automatically, yeah, dxp. So now this looks more like the Boltzmann equation, the Navier-Stokes equation, but it's not the Navier-Stokes equation because one thing is missing, right? What is missing? Yeah, on the right-hand side, something is missing.
Yeah.
What is missing on the right-hand side?
I can't remember it, but it's like the velocity terms, I think.
Yeah, you know, it's a diffusion term.
Yeah.
It's the viscosity. Yeah, diffusion of. So all we have here on the right-hand side is just the pressure. Yeah. So this here is called the Euler equation. And this week in the fluid dynamics class, I also noticed that everybody is familiar with the Navier-Stokes equation, but nobody seems to be familiar with the Euler equation, which is an older thing, but probably nobody is familiar with the Euler equation because the Euler equation is not. is not actually that useful, right? So it's not, you notice there is something missing, and this thing is actually important. So why is there something missing? Actually, we can easily explain that tau is not zero in reality, and this is what we assumed, right? So what happens if tau is not equal? So we can keep a lot of this thing, yeah, but just add the part that is missing. Because now equation can get a little long, unfortunately, so we'll have to be efficient in the way we write them down. So the right-hand side will stay the same, and on the left, I'm confused with left and right apparently. The left-hand side will stay the same, yeah, and the right-hand side will still have the pressure term. But then we get all the non-equilibrium terms together with tau. So what are the non-equilibrium terms? We saw there are 3 of them, yeah, for each moment that we had. So we had one dx, and this was for the moment m200, yeah. So we get here dt m200 plus dx m3. Now we count up again, so this is something that we learned. M210 plus the set M201. Okay? Now, in addition to this, we have tau times dy. Now, at this moment was M11, right? So then this will be dx M21 plus dy M120 plus dz M111. And the last one will be plus tau dz. Here comes dt M101 plus dx M102 plus dy M111 plus dz M102. Did I make any mistakes? Okay, it's difficult to read. M2 is. Okay, I hope I didn't make any mistakes. So this is the guide that comes in addition.
First term, I think, is dx M102. Shouldn't it be 201? Is that the next one, yeah?
102. Yes, you are, wait.
201.
Yes, thank you, yes. So, now all of this here, we call S to shorten a little bit this discussion. Now we have something that is, now we have this moment chain, and this moment chain will never stop if tau is not equal to 0, right? And this is what in the kinetic closure problem. So if you learned fluid dynamics already, you know about the closure problem of turbulence. Have you heard about the closure problem of turbulence? No? Probably you have, but probably you don't remember. They are of the same nature, they have the same origin, yeah? And so, you know, the Boltzmann equation and the Navier-Stokes equation describe the same reality. So at the end of the day, they all run into the same corner, right? Now, the Boltzmann equation runs into this corner actually a little bit quicker than the Navier-Stokes equation, but still it does. I mean, yeah, quicker. So it even before that, both of them run into the same problem. So the problem is whenever we want to write a differential, whenever we write a differential equation, is depending on a different differential equation of a new variable that we have to introduce. So inside this chain, yeah, all the equations that we can produce always depend on variables that are not known and for which we need more equations. And this is, so it will never, and this never ends, it's not closed. So this is what we mean by a closure problem. So we always need the next level or the next moment. The next order of moments. So we have to do something clever in order to get this chain terminated in some way. So now we look at these moments that pop up here. M300, yeah. So this again is of course M300 equilibrium minus tau dt M300 plus dx m now 400 plus dy M310 plus d zip, try to write more beautifully, M301. Okay, we'll see getting to the end already. And we have the other moment looks like M20 is M210 equilibrium minus tau dt. See, the annoying thing is that they become more and more and more moments. All of them we need to know in order to close our chain. So, and then there's other guys which I just won't write down because it's getting boring, right? So you can do this yourself. So if we have these equations, duck, 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 yeah, for which we need the next order of moments. So the hierarchy in here is infinite. Will never stop. So it does not stop. So how could we do it? How could we stop it artificially? How to stop this? Now we have to get a little bit creative in order to stop this, but only a little bit, because obviously the Navier-Stokes equation has kind of done it, even though we know that the Navier-Stokes equation is not completely correct, and this is also one of the reasons why it isn't. But we have an idea, namely tau. We said previously tau is 0, and we got to the Euler equation. Now let's do it a little bit different. See, tau is not 0, but tau is still small. Okay? So tau is small, but not 0. So then say that tau. Now we just say, you see, this is a bit contradictory. Yeah, tau is larger than 0, but we assume that tau square is 0, right? So this is what we do in finite differences all the time. So delta x is not 0, but delta x squared is 0, right? So let's try it this way. So if this is the case, what can we do? You see, all of these equations that we have up here have already a tau in front of them, right? So their non-equilibrium part will have tau squared in front of them, which we think is 0. So at that level, we will only depend on the equilibrium of these third-order moments. That's the idea behind it. So we can write that M300 is M300 equilibrium plus order tau. So that means we have again to compute I'm doing in time, 10 minutes, okay. We have again to write, to compute the equilibria of these moments of this Boltzmann distribution, square m divided by 2 Boltzmann t. Now we have to multiply this by xi by the power of 3 and integrate this over all the directions, and all of this will still have an order tau error to it. And what comes out is, I used Mathematica to compute this, 3k Boltzmann t divided by m into rho ux plus ux square plus something of the order of tau. So for the other guys, I get 1 M210 equilibrium. I get uy rho k Boltzmann t divided by m plus ux square plus something of the order of tau. And I also get M111 equilibrium is something of u, the rho ux, uy, uz. Okay? Now you see there are lots of terms that come with third order terms in velocity, but not all of them. For example, we have here uy times something here, which is kind of related to the pressure again. So this is the first order term in velocity. Okay, I have to make an announcement in the sense, first of all, we don't have a lot of time left, and even though we could use these things directly to derive the Navier-Stokes equation, I have to tell you that doing it directly is pretty complicated. It's possible, but it's complicated. For that reason, we will make some assumptions that are kind of reasonable for now, and just give us the equations more quickly that we are looking for. Yeah? So we do the assumption that the temperature is a constant. Because otherwise we would have to also solve an energy equation. And we also do the assumption that the velocity is low. Low velocity means that ux by the power of 3, so all the velocities, ux, uy square by the power, so these are third order velocities, right? We assume that they are 0 because the velocity is small. So this will, cancel out these guys here and this guy here completely. Yeah? Again, this is not necessary. We can derive the equation also with this and see that they in the end will fall away anyway. But it's much, much, much more complicated than what we are now trying to do in the last 5 minutes. So again, I called this guy up there, yeah, the addition to the Euler equation. I called this S. So I'll now only write this S in this format here. That is tau dx dt k K Boltzmann T divided by M rho. So this is the part that comes with the from the second order moment, is related to the pressure. Dx 3ux K Boltzmann T divided by M rho plus dy uy K Boltzmann T divided by M plus dz uz K Boltzmann T divided by M, and actually I have to get here something of the order of tau in addition, plus tau dy dx. So there is no time derivative here anymore, because the time derivatives of the other guys are all disappearing when we assume that the velocity is small. Yeah. So because we are now looking, yes, we are looking at this guy. So we'll end, yeah. So we end up just with uy K Boltzmann T rho divided by M plus dy ux K Boltzmann T divided by M plus rho plus something of the order of tau plus tau dz dx uz K Boltzmann T rho divided by M plus dz ux K Boltzmann T divided by M rho and something of the order of tau. Now you see, because there's something of tau times order tau, this will be tau squared. So, and now I'll call all of this here equal to Sx. I will call all of this here equal to Sy, and I will call all of this here equal to Sz. And when we recall the continuity equation, and put this into Sx, then all of what we have in Sx, so there's dx, ux, dy, uy, dz, yeah. This dx K Boltzmann T divided by M into dt rho plus this, so we have this guy here in front, so this is rho, yeah, so this is the continuity equation, this is equal to 0, so the entire thing here is equal to 0. Sorry, I made a mistake. This here is Sx. This is Sx. So what's, wait. Okay, no. No, I didn't, sorry, I'm, you know, 2 minutes before the end, I'm trying not to take too much overtime. I'm coming to the end, but sorry for being getting this a little bit disturbed now. What we actually have, we have once rho here, yeah. So we have once uy here, and we have once uz here, yeah. And in here we have 3 times the thing left, yeah? So then this and this and this and a part of that, will disappear. So what that means, sorry for being a little bit confusing here, is that all of this will end up, okay, now I see I even have to include the tau, otherwise what I'm writing is not correct. So Sx is tau dxx, so it's the x derivative of what is left here. So it's 2 times the x derivative, dxx, 2ux k Boltzmann t rho divided by m, and all of this together with O of the tau of the order of tau square. Yeah? And we decided that tau square is equal to 0. So if we combine this with the other guys, we can simplify the S to tau k Boltzmann t. So we'll put that what is everywhere outside and get dxx u rho plus dyy. So the other guys simplify in the same way. Ux rho. Okay, I'm not writing down the entire procedure. More like what is getting out. So we can isolate this part and have a reminder. So I isolate this part because I already know the Navier-Stokes equation and I know that I want to have this guy, and just see what else do we get. We get dx xu x rho plus dxy uy rho plus dz dx u z rho, and all of this together with the guy that we said is being considered to be 0. And now this can be written down in a more simplified manner as tau k Boltzmann t divided by m. So this here, this is the Laplace operator, obviously, right? So it's Laplace on u. A Laplace on ux rho. And the last one actually is a derivative of the divergence, right? So it's plus tau k Boltzmann t divided by m dx, and here we have the divergence of derivative of the divergence, and now we can put all of this. Okay, I'll get 5 minutes overtime, I'm sorry. dt ux plus, so this is now the left hand side, u times u x 1 minus m. So this is because we are using particle density and not mass density again. dxp plus tau k Boltzmann t divided by m into Laplace ux rho plus dx divergence u rho. Now, does this look like the Navier-Stokes equation?
Yes.
And actually, if we consider it completely incompressible, we would also get rid of this thing, because then divergence is disappearing. And this guy here, now we have to identify with the viscosity. So now what you see is that this tau is basically proportional to the viscosity in the Navier-Stokes equation, and by adjusting the tau in the BGK equation, we can adjust the viscosity. So now this here, finally, for today, is the Navier-Stokes equation as derived from kinetic theory. Okay, let me see. I'm 4 minutes over time. Sorry, I'll stop the recording. Always doing this wrong.